Hi everyone, this is Tom with a video on getting started with regression in Jamovi. So my objective in this video is really to make you more comfortable with the analytics that you'll need to do for the Springfield-Clifton Unified School District case, your first case analysis. So I'm going to use a data set in which I'll perform many of the same analytics that I might do with the SCUSD case. I'll explore the data, I'll create a dummy variable so that we can do some regression modeling. We'll take a look at the fit of the model and the impact of the different covariates and make some interpretation. And then we'll also do a dive into some deeper techniques. We'll use what I call a block entry method of regression building that will allow you to compare different models of covariates on the dependent measure and see the incremental value or the incremental changes in regression as you include different variables in the regression model. We'll also take a look at the impact of interactions on dependent measures and how you can test for interaction effects in Jamovi. Now, in doing so, I won't be going into great detail on the mathematics of regression or on the bigger picture of what regression represents. There are some great videos that are available that do that job better than I could. I would highly recommend, if you want more of a background on regression, that you stop here and you view my colleague Paul Green's Introduction to Regression. There are a few other links you can see here that I'll provide as well, and I'll include these links on the page where you got the link to this video. So let's begin by giving you some context and background on the data set that I'll be using to demonstrate these analytics. I have a data set with 10,000 records in it that detail student academic performance in a number of different areas. So the data set that I has for about 10,000 students their previous scores on a test, how many hours they spend studying, a variable on the number of sample tests that they've used to practice, the average amount of sleep that they're receiving, and whether or not they're involved in extracurricular activities. That's on a yes-no scale. So those are the independent variables in the data set. The main dependent measure is a variable called performance index. This is kind of an evaluation of the student's overall rigor and academic kind of inclination. Now, with those predictors and that DV, dependent variable in mind, here are the hypotheses that I want to test. Now, this is a step that you'll take as you explore the SCUSD data set. You'll want to get familiar with the data and then think about, in relation to the questions that you're answering for the case, what hypotheses do you have about what's going on in the data set? That will then indicate the direction that you want to take your analytics. Now, here are the hypotheses I came up with that I want to explore with this student activity data set. My first hypothesis is that previous performance on tests is going to be significantly related to their performance index scores. That is, how well they performed in the past is going to be a good predictor of how well they'll perform in the future. My second hypothesis is that characteristics like study hours, number of hours spent studying, whether they practice sample questions, and how much sleep they're getting, add significant predictive power on top of the previous score that I mentioned in hypothesis 1. So I predict that those variables will have an impact beyond the previous scores. My third hypothesis is that if a student is involved in extracurricular activities, I anticipate that is negatively correlated with performance index. The last hypothesis is that the impact of hours of study on the dependent measure of performance index will depend on the amount of sleep that a student gets. If a student isn't getting a lot of sleep on average, then the amount of time spent studying is not going to have as much of an impact on performance index as if a student gets lots of sleep. Then those study hours, I say, will add value to them as a student. So we're going to test the interaction between hours of study, average amount of sleep on the performance index score. So those are the hypotheses we're going to test. Now let's go into the Jamovi tool. Let's pull up the data set and let's explore these hypotheses. So here I've opened up Jamovi, and here we see on the left the data in the student performance data set. the hours slept, previous score, here's extracurricular activities, yes or no, number of sleep hours, etc., etc. Now, let's do what we might normally do here, which is to explore the data with some descriptive statistics, maybe some correlations, some plots. So we'll go to analytics, and I'm not going to do everything here in the interest of time, but I'll just hit some of the basics. Let's go ahead and include all of our variables here to get the descriptives. Now, to make this a little bit easier to read, I'm going to change it from variables across columns and make the variables as rows. So here we see the variables vertically displayed, 10,000 cases, nothing missing. So let's remove the sample size and the missing descriptive so that we can focus on more important things. So here's mean for hours studied, median of 5, and it's with a range of 1 to 9. Previous score is the score on a previous exam or test. The average was 69.45, a median of 69, and ranging from a low score of 40 to a highest score of 99. Extracurricular activities is a text variable of y or n. So if we click on frequency tables, we should be able to see here the spread of those who are involved and not involved in extracurricular activities. We see it's about 50-50 in terms of those who choose or choose not to be involved in extracurricular activities. And going back up, sleep hours, 6.5 on average, ranging from 4 to 9 hours on average. Sample question papers practiced from 0 to 9. And performance index average of 55.2 or median of 55. And a minimum value of 10 and maximum value of 100. So that's the range for that. And as we take a look at the frequencies, I don't see anything anomalous. 1 to 9 hours studied. Here's number of sleep is 4 to 9, and sample question papers from 0 practiced 0 to 9. We take a look at some plots. We might check on the distribution of these variables. Here we see our study is pretty flat across the board. No curve there. We see the plot, pretty flatly distributed from 1 to 9. Here's previous score, not quite normally distributed, a bit flat across the top. Same thing for number of sleep hours from 4 to 9. Here's the median at 7 there for that. Sample number of question papers practiced, again, fairly flat, even those at the lower end, similar numbers from the lower end to the high end of that scale. And here we see a somewhat more normal distribution for the performance index score. So more of a bell-shaped curve there, and that would be attested by the box and whiskers plot as well. So nothing jumps out at me there. Let's do one thing. Let's explore this idea of whether or not extracurricular activities is negatively correlated with performance index. So let's just do this. We'll do it with the t-test. Let's take performance index as our dependent measure, and we're going to split that dependent measure by whether or not people are involved in extracurricular activities. And we'll include the mean difference and the descriptives and the effect size as well, so we can see the meaning of any difference. So here's the t-test. We see that the mean between those who are involved in extracurricular activities is 55.7. For those not, it's 54.8. So the mean difference is fairly small. And because of the number of people in the analysis as reflected by the degrees of freedom here, that t-test is significantly different at p.014. But we see that the effect size, that difference, is not very meaningful as the ratio of mean difference to the variance, the pooled variance of the two of the extracurricular variable is not very great. So yes, the means are different, but it's not a lot of meaning that we can put in that difference because it's so small. Now let's take a look at correlation coefficients. So let's do a correlation matrix. Now, unfortunately, we can't include extracurricular activities in the matrix because it's a text variable. But what we can do is stop at this point and convert that text variable into a categorical variable. And we'll do that by going to data, and we'll transform that extracurricular activity variable into a dummy variable, a dummy coded variable. So I'm going to use the transform function here. And I'm going to call the new variable extra.curriculum.dummy. And the variable that we want to transform is the extracurricular activities variable, which is either a yes or a no. And we'll need to create a transformation to convert it from y and n, yes and no, to 0 and 1. And so we'll add a recode condition, which tells us that if the source variable, extracurricular activities, and we'll define if it equals yes, we'll give that a 1. Else, if it's something other than yes, which in this case can only be no, we'll use 0. And as I hit enter, we see that a new variable has been created. Here it is, extracurricular dummy. So now that we have our variable dummy coded, let's conduct that correlation matrix. Let's include all of the available variables, and let's flag those that are significant. And what do we see here? Let's take a look at some of the interactions of variables and their correlations. So here's performance index with previous scores, and we see that it's a very high correlation, 0.915. Doesn't get much closer to 1 than that. It's significant, of course, at the 0.001 level. So a strong relationship of previous scores to performance index. It does seem that past performance predicts future performance. If we take a look at that performance index variable against other variables in the data set, here's hours studied, and we see that there is a positive correlation between hours studied and their performance index score. It's quite significant. Extracurricular activities, very small correlation. It is statistically significant, but that's due to the number of people in the equation. That's not a very meaningful correlation. We can say the same for sleep hours and the number of sample questions practiced. Both are statistically significant. They're not due to chance, but very small. Let's look at the intercorrelations among the independent variables. So hours studied, extracurricular, sleep, and sample questions. And when we take a look at that, we see that there isn't much correlation between the hours studied and the other variables. Here's a significant correlation between extracurricular activity and sleep hours, but it's very small. So in terms of the correlation, in terms of the regression that we're going to conduct, we certainly want to include the performance index, certainly want to include hours studied. And we might want to include these other variables as well because they are correlated with the outcome measure, although they're operating quite independently from one another. There's not a lot of variance shared, it seems, between them. So that's a good enough reason to include them in our regression equation. With that in mind, let's build a regression model. So we'll go to linear regression, and our dependent measure is performance index. Now let's include our continuous variables, or at least what's described as continuous variables, here in the covariates box. We'll use previous scores and hours studied. We'll take sleep hours and sample question papers practiced. Now, the extracurricular activities variable is categorical. It's yes, no. So we will include it not in the covariates section, but in the factors section. So the factors variables are those that are continuous or treated as continuous. And factors are for categorical variables you want to include in your regression equation. So what do we have as a result? Here's our model where the R is quite high with all of these variables included, 0.994. You square that, you get 9.989, which is fairly high, very high. There's a great fit between these variables and the prediction of the dependent measure, performance index. Now let's include an additional variable here. You'll certainly want to do this with the SCUSD case and regressions you perform there. We'll include here an adjusted R. The adjusted R statistic is an adjustment of the R squared, just as the name implies. It takes into consideration the number of variables that you have in the equation and the number of people in the equation. Now, in the SCUSD case, if you include all of the predictors in a regression model, I think that would come to 13 or 14 variables, something like that. That's quite a few. And so the adjusted R might give you a better idea of the fit of all of those variables to the dependent measure. And so in that case in particular, you'll want to pay attention to the adjusted R. As we can see here, there's no difference because of the small number of variables and the sizable number of people we have in the data set. We see that the largest of the covariates is hours studied with a covariate of 2.853. And of course, all of their t values are significant. So each of these covariates or predictor variables, their covariates is significantly different than 0. Therefore, it did not occur by chance. We can include it in our model with confidence. We see the previous scores also had the second largest covariate at 1.018. We do see that extracurricular activities, if you're involved in it, it does seem to have an impact on your performance index. So here we have a model that's fairly good at predicting what a student's performance index score would be. The fit of your regression model to the dependent measure, which is performance index here, is dependent on the variables that, of course, you include in the equation. If you remove one of these covariates, the overall fit of the model will change. The overall R will change. If you remove a coefficient that has a significant impact on the dependent measure, like, say, previous score or hours studied, then you would expect the model to change more dramatically than if you were to remove something with a smaller coefficient, like sample question papers practiced, for example. It's also true that sometimes the order in which you include the covariates in the model can affect the fit of the model itself. To help you compare different models, that is, regressions with different combinations of predictors, or to examine the impact of the order in which you enter the covariates in the model, I'm going to show you a Jamovi function called block entry. And essentially, what it allows you to do is to set up several models that sequentially allow you to add variables into the model. And you'll see then the differences or the impact of changing covariates across different models. It'll be easier when I show it to you to understand than my explanation. So let's go to Model Builder, and we'll pull down the menu of opportunities here. And as you can see, here on the right is something called Block 1, and in Block 1 are included all of the independent variables that we've included in our model: previous scores, hours studied, sleep, sample, and extracurricular activities. Now what I'm going to do is I'm going to remove all of these variables except for previous scores. So let's remove extracurricular, all of them, and now the only predictor in our model is previous scores. And here you see the model reflecting that. And in this model, the R is 0.915, very high. The R squared is smaller than it was in the previous model with all the variables included, but still fairly high, 0.838. There's the adjusted R square, same thing. And we see previous scores is, of course, a significant coefficient. Now we're going to add in additional variables. Now you'll recall that I suggested I had a hypothesis that study characteristics like number of hours you've studied and sleep hours and sample question papers practiced, those have an effect on performance index, a prediction on performance index above that of previous scores. So I'm going to now add those three variables into the equation. I'm going to add a new block to do so. So in this block number 2, I'm going to take hours studied, sleep hours, and I'm clicking the first variable and then hitting Shift on my keyboard and clicking the last variable. And now I'm just dragging them over here to the equation. Oops, and it included some interactions I didn't want. There we go. So now let's see what we have on the right. What we now have is a model that has previous scores and the three variables that I just added, and it's calling it Model 2. We can, using the drop down here, go back to Model 1 with just previous scores in it. But let's go back to Model 2. And what's most interesting really is what you see here above that table. Here we see now two models. We have Model 1 and Model 2. We see the R and R squared and adjusted R for each model. And we can see that this Model 2, with these three additional variables in it, has an adjusted R 0.988, which is higher than the model that only contains previous scores. And now this next table gives us the impact of that comparison. It compares the variance explained by Model 1 with the variance explained by Model 2. The difference in adjusted R is 0.151. And that difference is statistically significant when we apply an F-test to it. So what we've learned is that adding these three variables adds a significant amount of predictive power or variance predicted on the dependent measure. Therefore, we might want to say, well, previous score works pretty well, and it's a mighty fine predictor, and it's very high, but we can get even more predictive power when we include these other characteristics around the students' study and sleep habits. Now, the final question we ask is, well, what is the relationship of extracurricular activities to this model? Does it impact the prediction of performance index significantly? So now we're going to add a third block. And in this third block, we'll simply include a remaining variable that's not in the data set. So I'll click on it, highlight it, and I'll click the arrow, and now we have a third model that includes the extracurricular activity variable. And when we look at the comparison above, now we have three models with R and R squared compared, and we see that the difference between models 2 and 3 is de minimis. There's not really much there. In fact, the difference between the models is 2.54 to the, what does that mean, fourth power? And while the number of cases in the analysis makes it statistically significant, this is not very meaningful. So what we've learned here is, yes, it is significantly different. This covariate adds significantly different from zero predictive power, but it doesn't add much to the overall model. In the interest of parsimony, which is the idea that we would want our regression models to explain as much variance as possible while minimizing the number of variables in the equation, I would suggest that our final model selection should include every variable except extracurricular activities. Now, again, you might want to think about this in terms of the SCUSD case, because you have a number of predictors. There are several dependent measures you're going to have to choose among. And you're going to need to, and what you might want to consider recommending for Simon Ford, or the protagonist in the case, is what is the best model for Simon Ford to use in selecting teachers to his school district? And how can I get the most predictive power while keeping the costs and the time required to administer all of those, to gather all of those data, minimized as much as possible? I think that's a consideration. And using this model building approach, this block approach to creating regression models and comparing them with one another might be quite useful in that. Let's talk about interactions between variables. Now, an interaction between variables means that the effect of one variable on an outcome measure depends on the level or value of another variable, which implies that the relationship of the predictor and the outcome measure isn't constant, and it changes depending on this third variable that's involved. So my hypothesis for this case is that there is an interaction between hours spent studying and hours sleeping, such that the more sleep you get, then the hours you spent studying have a greater impact on your performance index compared to situations when the student's not getting a lot of sleep, in which case whatever hours they're spending studying is probably not going to be as effective. That's my hypothesis. I believe there's an interaction between hours spent studying and hours spent sleeping, and that it impacts the relationship of those variables to the dependent measure of performance index. So with that in mind, let's go back to Jamovi, and let's see if we can include an interaction term in this model and see if it is significant and if it's significantly adding any value in our prediction of the performance index. So what I'm going to do here, I'm back in the block entry view. Now, we know that we weren't too keen on extracurricular activities as a predictor, so I'm going to remove that model. So now we're back to just two models. And I'm going to include now an interaction effect. And we'll see what the relationship is between that and the dependent measure. So to do that, what I'm going to do is take the two variables I think are intersecting, That's hours studied and sleep hours. And I'm going to include those in an interaction. What I've done is I pulled down here by this menu, by this arrow, I pulled down a little down menu, drop menu, and I'm going to select interaction. And now that is included in, and you know what I'm going to do? I'm going to actually add a new block. We want to add this to block number 3, and that's where I'll add. So I've gone back, and now I'm going to do it again. So in block 3, I'm going to add that as an interaction. All right, so now we're back to having 3 models. First model just has previous score. The second model has previous score and the 3 study characteristics variables. And in the third, we're including an interaction variable. And when we look at that interaction, let's first look at the R squared. And we see that it has our interaction variable has not added any predictive power to the model. There wasn't much predictive power left to be explained, so that doesn't surprise us a great deal. We see that the difference between model number 2 without the interaction and model number 3, the interaction, is very small and is not statistically significant. That's how small it is, even with 10,000 people in the equation. And we see here that as a covariate, a very tiny covariate, and it is not statistically significant. So what we can say here is that there is no interaction between those 2 variables, at least not to a degree, that it influences the prediction of the performance index. So I think that's all I've got for jumping into multiple regression with Jamovi. Certainly come to office hours if you have questions or if there are other aspects of regression that you'd like to explore.